Bueno, entonces continuando con la sesión de geometría, tenemos el gran placer de álgebra y geometría, disculpen, tenemos el gran placer de tener al profesor Cristian González, que nos va a dar su charla en inglés y se llama The Algebraic Brauer Group of a Pinched Variety. Cristian, por favor, adelante.
Okay, thanks for the invitation. And I'm going to talk about some singular stuff, okay, singular curves, essentially. Okay, I'll try to talk about singular curves. But first I have to define the basic objects that I want to discuss. So here we're going to have K is a global field, a global field. So that means either K is a finite extension of Q, the rationals, or K is a finite extension of the rational function field, or P is a prime. So this is a finite field with P elements. Okay, this case is very interesting. Well, this too, this is classical. Okay, lots of people care about number fields, but I care a lot about function fields too. Okay, and usually this case is very interesting and very difficult. So I'm going to recall the Brauer group of K, which is the group of equivalence classes of Azumaya algebras. It has a very nice interpretation, but I'm going to use the cohomological interpretation. So this is an H2, K with coefficients in the sheaf of the multiplicative group scheme. Okay, so this K is the global field. And well, this global field, we have completions. So we can complete this global field at the primes of the field. So we have the completions. These are local fields. So they are either finite extensions of Q, P for some prime P, the p-adics, or is a finite extension of the field of Laurent series. Okay. So that's a local field. So here we have a power series. We can try to solve some polynomial equations in power series first, which is easier, and then try to look for global solutions, actual polynomial solutions. Okay, that's what this talk is about. Well, this group is usually hard to compute, difficult, but these are very nice. Oh, so nice, because they are just isomorphic to Q over Z. Okay, so the Brauer groups of the local fields are easy to compute, and there is an invariant map here, classical invariant map of local class field theory. Okay, that didn't come out very nicely, but it says, well, let me try again. Oh, I forgot this guy has a magnetic personality. Okay, good. So that's the invariant map of class field theory. Okay, so this is the setup, but now I'm gonna consider a proper variety. Let X be a proper K variety. Not necessarily projective, but projected, it could be projected, but in general, it's proper. Let X be a proper K variety, which means that it is actually, variety means here, proper and geometrically integral. So geometrically, over the algebraic closure of the field is going to be reduced, no nilpotents, and connected, okay, or irreducible. So proper and geometrically integral or finite type, of course. K scheme of finite type. So that's so I'm going to work with the proper varieties, not affine stuff. Okay, affine case is much more difficult. So this one is hard enough. Anyways, so what am I concerned about? But not any proper, such that the polynomial equations that define X have points on the over the local fields. So we have solutions in power series. Okay. And so this is going to be assumed to be non-empty. So I always have local points, okay? And so the question is, so this is the question, does X have a K point, the global point. So that does X have a K point? Well, this means that the group, the set of rational K rational points, whether or not it's empty or not. Okay, so that's the question. Do we have polynomial solutions of the equations that define X? If we would have solutions in power series, do we actually have polynomial solutions? That's a $10 million question or more, 100 million. Okay, so here, as we have a Brauer group of a field, there is a generalization of the Brauer group of a field, and we can also talk about the Brauer group of X. Actually, this is called the Brauer-Grothendieck group because Grothendieck defined this group. It's a generalization of that, but it admits a similar cohomological interpretation. Now it's going to be, instead of Galois cohomology, it's going to be a Tal cohomology. So when I take X equals spec of K, I get this back. Okay. So this is a more general version of the Brauer group. And this Brauer group, why is this guy important? Because this guy plays a role in obstructing or telling me when this is going to be empty or not empty. So it plays some role. It doesn't decide the whole thing, but it does play a role because there's a pairing called the Brauer-Manin pairing. Oops, sorry. So there's a bilinear pairing. This set is not empty by assumption. So all V, and I take the Brauer group of X here, and I can define a bilinear map, a pairing. So here I take the local solutions of my equation, take a class here, a cohomology class. So here, this is the group of equivalence classes of Asomaya algebras defined over X. It has a similar interpretation. So here we have, we take this sum, which is actually going to be finite in spite of appearances. It's going to be an invariant map and PV star Z. Okay, so this PV star, what is this PV? PV is a rational point. So I'm viewing PV here, this PV, I'm viewing PV as a, as a morphism of scheme spec KV into X. And so I can take if I have a cohomology class here, I can use, this is a big X, okay, big X. If I have a cohomology class Z or P or high or whatever you call it, this one in here, I can pull it back according to this morphism, and I get a class on spec KV, and then I can apply the invariance, and I get this infinite sum, but it's not infinite because most of them are trivial, zero, so it's a finite sum. And so you can call this PV chi. Okay, that's the pairing. Okay, that pairing, why is that pairing important? Well, I mean, why does it play a role? Oh, because there's a big theorem in class field theory that says that when you take, because there's a diagonal map, the K rational points map into this product, okay? Just diagonally, because K is containing KV for all V. Okay, you can take that map, and by a big theorem in class field theory, that the image pairs trivially with this guy. So it maps to zero. Okay, so that's a theorem from class field theory. Okay, so let me write it properly here so that you have a visual explanation of why this is important. So we take this set. Let me define it. This is a subset of the left-hand side. It's just a subset of P's that are killed by everything. By every class in the Brauer group. And as I said, because of this theorem in class field theory, so this set is contained here because the points that live in here, when you map these into here, they get killed by this pairing because of that big theorem. And so we have a so-called Brauer-Manin obstruction to the existence of K rational points because if there are no points that live here, namely, means if this is empty, if there are no points that are killed by everything, if this is empty, then this guy is empty too, and I have no solutions, and there's nothing. So this guy x of k would be empty in that case. So that's why the Brauer group plays a role, important role in arithmetic geometry. And I'm not here to talk about this problem because it's a huge problem, and I don't have much time here, even if I could. But I only want to say the following. This is called the BM pairing, Brauer-Manin. I don't have any space. Here we can erase this guy. He played a role. He played a role for a while, and now I'm saying goodbye to it. So we call it BM, Brauer-Manin, because Manin Yuri Manin was the first to realize this in the 70s, long ago. Okay, so the BM pairing, let me read you what I wrote here. The BM pairing has been much studied when X is smooth, when this is a smooth proper variety, and K is a number field. So you can find lots of papers where they discuss, lots of experts discuss the Brauer-Manin pairing for smooth varieties over number fields. Now there's increasing interest in studying the same Brauer-Manin pairing for function fields, but still for smooth varieties. And there are not many papers about that. There are a few. They're hard to find. Okay, but that's just starting. Okay, but there are no, as far as I know, there are no studies when X is singular, when this has some singularities. When X is singular, then K is either a number field or a function field. So there's very little that has been done in that case. And in this talk, I'm just going to talk about the Brauer group of certain singular curves, okay, of a singular curve in general. Why? Because any information that I get about the Brauer group and for singular curves, I can apply it to study the Brauer-Manin obstruction for singular curves. The Brauer-Manin obstruction for smooth curves has been studied over number fields and probably also over function fields. But the singular case, as far as I know, there are no studies about that. So singular curves and the Brauer-Manin pairing are two things that mix well or interesting, but it's very difficult to, the smooth case is difficult. The singular case is also, it's even harder. But still, the Brauer group of a singular curve has not been studied much. I mean, if you try to look for, you go to Google the internet, Brauer group of singular things, singular curves, or singular varieties, you'll see that there are no many papers, and the few that there are usually work over an algebraically closed field. So you can certainly find information about the Brauer group of a singular variety over an algebraically closed field. Maybe characteristic 0. Okay, so you can find that. You can read it in the Gonzalez-Aviles book, the book on Brauer groups that came out a couple of years ago. You can find some there. De Meyer and Timothy Ford have written something on singular Brauer groups of singular varieties over an algebraically closed field. My good friend Martin Bright at the University of Leiden, he has studied Brauer groups of singular Delpezza surfaces. Okay, so but beyond that, there isn't much done. So I'm just getting into the singular curves because it's interesting and because there's little that has been done there. So I'm just trying to, oops, this doesn't work very much. I'm just trying to increase the literature on singular stuff. Okay, so that's what I'm going to talk about now, singular. And to get to the singular curves, I need a certain construction. So this is page 2, good. So as a necessary preliminary step to study the Brauer group, it is easier to study the algebraic Brauer group, which I'm now defining. This is called BR sub 1x. So this is the kernel of the whole Brauer group, and the classes that are killed when I go to the separable closure of the field. Okay. So all the classes in here that are die when I pull them back to the separable closure. This one is X times separable closure of the field. Okay. If the field is perfect, this is just the algebraic closure, but it's not going to be that in general, you know. And I do care about imperfect fields because the function fields are imperfect. So this is the this Brauer group, this algebraic Brauer group is easier to study because you can use cohomology in degree 1. Remember that this is cohomology in degree 2. So you can use cohomology in degree 1 to study it because there's an exact sequence. So I call, instead of SEP, I can call S. Okay, it's easier to write. The Galois group figure acts in here, and you can look at the invertible sheaves that are fixed by the action of Galois. Okay, so BRK, BR1, BR1X group algebraic, and then I land here in H1K. This this is an H1, and with coefficient in the Picard scheme. So it's a Picard scheme 0. Nice. So I can study this guy by viewing it inside here. So this group is important, and also have the Brauer group of the field. Usually I can compute this Brauer group up to the Brauer group of the field. Okay. So my formulas will involve Brauer groups of fields, which are simpler. They are very difficult by themselves, but they're simpler than Brauer groups of varieties, of course. Okay, in the construction that I mentioned is the following. You can take, how do you produce singular curves? So let X be, actually, I can do it in higher dimensions. So let X be a proper variety of any dimension, but we will be concerned with the curve case. Let X be a proper, as before, same as before. Okay, no, I'm not going to repeat that. And but with finite, with not too singular, with finite non-normal locus. So there are only, all points are normals except finitely many. With finite no normal locus. So it has a finite number of singular points that are not normal. That's all. And so let's call this non-normal locus a finite K-scheme, Y. And then there's a construction that can recover X, the one you care about, you can recover it from its normalization. You take the normalization for curves, usually for curves, for many, not for all, but for many curves, the normalization resolves the singularities of a curve. So this one is going to be, not always, but usually going to be smooth in many cases. The normalization is going to be smooth. The problem is the imperfect base field case, function field case. Okay, so there's a so-called a pinch diagram. So you take the inverse image of non-normal locus. So you get here an induced map. So you get an induced map. This is going to be an induced morphism between finite K-schemes. Okay, finite K-schemes. Okay, this is the non-singular. I mean, this is the singular locus, the non-normal points. Let me write it correctly. Okay, the best way I can. Okay, so this is it's called a pinch diagram. A pinch, it's not actually, it's a particular type of pinch. There are more general ones. This is called the conductor square. The conductor square of the normalization. Okay. So as I said, this will have many singularities, and the normalization will resolve many of them, except in the perfect function field case. So where's my cup of water here? Okay, so And so what I want to do, I want to use this pinch diagram to find the algebraic Brauer group of this guy in terms of the algebraic group of this guy, which is usually going to be smooth. Not always, but usually. Okay. All right, that's good. So the problem is, it's a basic question. Of course, I'm not going to prove anything. I'm just going to state my main theorem. And if I have the time, show an application that will hopefully convince you, oh, this is interesting. Okay, so basic question. What are the kernel and co-kernel of the pullback map? The normalization, the pullback from BR1X into BR1X normalized. So that's my basic question. Because then I could try to study the Brauer-Manin obstruction for curves, for instance, if I have some information about the situation over for a smooth curve, and I can then tackle the singular case via this map. So this is important to know what the kernel and co-kernel of that map are. And this is actually, I can do this because of an excellent, nice, beautiful paper written by Michel Brion. Okay, I already thanked him. Okay, I told him that thanks to his work, it's possible that I can write this. Okay, so that's what typical in mathematics. You know, we stand on the shoulders of others. We use the work of other people, and so the beautiful sequence that or paper that I was mentioning about by Michel Brion. He is one of the top experts on algebraic groups in the world. Michel Brion, he produced this excellent exact sequence. He can tell you, given that pinch diagram, the conductor square that I mentioned, he can tell you what the difference between the Picard schemes are. He didn't discuss the Brauer group, but he discussed the Picard scheme. So he tells me that the Picard scheme of the normalization is related to the Picard scheme of this singular guy via there is some garbage. No, let's not call it garbage. Some defect. Okay, so some defect introduced by the singularities. And what is B? B is the did I write it here? No, I didn't write it, but it's just the X. Yeah, one of those, X or N. I don't want to call, maybe N. And A is one of those. Maybe I have them backwards. I didn't write it here. Sorry. Okay. So these are just the groups of they are fine range of the varieties. Okay. And what is this guy? What is this relative unit group? This relative unit group is just the Weil restriction of the multiplicative group scheme up here divided by the Weil restriction of this guy. Okay. And so thanks to that and to the long exact sequence that I showed you 10 minutes ago here, when I said that you could study this guy via homology in dimension 1 of the Picard scheme, then I can use that sequence along with this one. Of course, I have to use scissors to cut some exact sequences apart, take them apart, take this exact sequence, shorten one here, then assemble them and get a new one, and then get this theorem. Okay, and so with this theorem, I will end my talk, okay, because I just want to present what the main result is. It's actually a particular case of the main result, but I don't want to get too technical into this talk. Okay, no, I don't want to get too technical, and just state the result. And you'll see that it's not very ugly. It's very nice, in fact. Theorem. If, I didn't find the index. If the normalization has a 0 cycle of degree 1. So this is weaker than having a rational point, okay? It's weaker than having a k rational point. But I'm talking about the normalization, okay? After you apply the normalization, if you find the zero cycle of degree 1, okay, then there exists an exact sequence singular points, the non-normal points, intersections of all the points that live on the top and map down to y of relative Brauer groups for fields. This is the kernel of the map from the bottom field to the top field. But these are Brauer groups of fields, so these are more manageable than the whole thing, the Brauer group varieties. And then I get BR1x, and then I get BR1x to the n, and then I get here an H2, which is mysterious for the time being. I know what it is. I know a lot about the structure of this guy, but I can't talk about that now. But anyways, but here's my map. So I can tell you what the kernel is using only Brauer groups of fields. Simpler, okay? And so you can, and this is new. I haven't seen it, okay? And I don't have the time to show you other things, but I can do other things. I can find other. I can determine. For instance, to finish, remember this map? I can tell you what this map, the co-kernel of this map is known over local fields. Okay, the index, this index, how big this guy is injection to. This guy is a subgroup here, and over local fields, it is known what the index is. The index of this group into that is the index. I mean the greatest common divisors of all the fields where you can acquire a zero cycle of degree 1, etc., etc. This is known for smooth. I can tell you what the index is for any singular curve. As an application, but I don't have the time. That will be in the paper coming, which will be published maybe 2 months from now because I've been so busy doing other things, man. I'm sorry. But anyways, that's what I wanted to tell you. I hope I didn't bore you to death. And if you have questions or complaints, criticism, okay, everything. I accept everything today, okay? Thank you.
Ok, gracias, Cristian. Un aplauso a Cristian.
Gracias.
¿Ya? Imposible no estar entretenido con tu charla, Cristian. Imposible.
No estuvo muy complicado, ¿no?
Sí, pero eso es usual contigo. Así que...
Vamos, Cristian.
Bueno, ¿alguna pregunta, algún comentario para Cristian? Ya.
Cristian, en ese nivel de abstracción que trabaja, ¿se pueden hacer ejemplos? O sea, ¿puedes partir con un X bonito, chiquitito, que te dé luces?
Okay, tranquilo. Ya entiendo. Tranquilo. El problema es el tiempo. The problem is the time. Okay? This is a singular curve. Esta es una curva singular, una cúspide. Mucha gente la conoce. Okay? Entonces, hay dos tipos de... Esto lo voy a decir en español, no importa. Entonces, esta es una típica curva singular. Okay?
Cristian, si quieres dejo de grabar. No sé qué prefieres.
Yeah, just stop recording.
Stop recording, okay.
Yeah, because